welcome to my talk called Shaping the Clouds, Gentle Introduction to TypeOps. Gentle is, I hope it will be gentle, but I fear that it's an insider joke. But we'll try to do it in the least painful way possible. I'm Łukasz Biały. I'm a Scala developer advocate, so if you have any issues with Scala, you can always contact me and we will try to do something for you. I'm also principal software engineer here at VirtusLab, and I dabble, well, in Scala, functional programming, distributed systems, and DevOps. You can find me on those channels if you want to contact me, and let's go into the presentation. So we have a small agenda. This isn't a presentation about any meteorological events or objects. We are not going to talk about weather. This is a talk that is primarily about building robust, reliable systems, not just applications, whole systems composed of many applications, and clouds are, unsurprisingly, I hope, APIs that allow us to programmatically set up infrastructure on which our code will be executed, or possibly that our code will use, like managed databases, for instance. So the presentation itself is definitely about the DevOps domain and the tools that we use in that domain. But since the talk is called Shaping the Clouds, we should probably establish first what shapes we have in mind here. So what does it mean to shape in this context? And therefore, before we talk about the status quo of DevOps, we should step back to the familiar world, I hope, of application development just for a moment and talk about things that we already found out to be true and very useful in this domain. So things that I have in mind, shapes, are obviously types, and I hope it's not a controversial take anymore, that types and type checking do actually help software engineers to build more robust software. I think they help us to scale the development process, and they help us to reify, so write down some rules, invariants, and expectations about code that we want to have checked so that we don't make mistakes. I also hope that we can also all agree here that type systems are in fact helpful in preventing whole classes of possible programmer errors this way. So I have some small snippets of Scala code, nothing fancy, just to show you the very basic issues that type systems actually help you to avoid. So this small program, it does nothing really interesting beside creating this instance of some class. And as you can see, we have just switched the places of the arguments, and the compiler, in, I hope, unsurprising way again, helps us to detect this problem. Same happens if we forget to provide one of the arguments, or if we have a more involved shape of things. We have a structure. If we pass invalid shape, invalid class into the constructor of another class, that gives us a nice error that we are mistaken. So this is a very simplistic set of examples, but I don't want to go into very gnarly examples with generics and things like that. We could go there, but I hope you get the gist. Types prevents errors at scale, and we are so used to them already that we just take them for granted. We expect type checking to happen. So if you have experience with type checked languages, it is quite an odd experience to go into a code base, existing code base that is written in a language like Python without types or JavaScript. And you quickly find out that, oh wow, there are things that I can't understand what is happening here in this code base, because there is no guiding hand of the compiler anymore. So we have this guiding hand of the Scala compiler when we're working on our apps. So in our application domain, we have the compiler checking everything for us. But then we leave this context. we go over the boundary of an application. We start thinking about the environment where this application is going to run. We move from the application level to the infrastructure level, and there's usually something else that is doing the work of managing this environment for us. Probably something like Terraform in most cases. So we can take a look at how this looks like with something like Terraform. So this is like a run-of-the-mill snippet of HCL that deploys a Scala application on AWS ECS, so Elastic Container Service Platform. I would like to ask the audience, how many of you are familiar with Terraform? Hands up. Okay, it's quite a lot. How many of you do have PTSD? Okay. Okay. I have to say I'm not a huge fan of HCL, but I have to admit that it's not the worst thing on the market. There are YAMLs from Kubernetes, for example. So those languages are not programming languages, right? YAML or HCL are not programming languages. They are just configuration languages. And they don't really allow us to express any invariants. They have some things built in, but nothing that we know from the application programming level. So HCL, for example, is completely unaware of what this application actually does. It has no idea how it does it, what it expects from the environment. And you have to take this knowledge from your head and then rewrite this to HCL and, well, Terraform apply. Oh, it doesn't work. So it is completely ignorant of what the application requires to run. It is also ignorant of the interfaces the application will expose. You have to remember about those things. And in many cases, this is like a cross-domain discussion that has to happen. You have DevOps specialists that have to be made aware by application programmers that there are some invariants, there are some rules about how this application has to be executed, how it has to be configured, how it has to run, what is the environment in which it has to run, what it expects from this environment. So we go from this sane way of thinking about encoding invariants and rules of the application, and we go to this world where everything is, well, it's probably in the documentation in GitHub somewhere, or maybe there's a piece of documentation in Confluence. So all of that is suddenly thrown away. There is no more type checking, no guiding hand of the compiler. So there are some ways to improve that. There are some efforts to make applications more robust, to improve the type safety over the boundaries. For instance, for protocols, we have protobufs, we have Thrift, Smithy, Avro. We also have open API specs for HTTP REST APIs. We have contract testing to develop contracts between consumers of the APIs and the creators of APIs. But all of those things are like bolted onto our code. They are something that is beside the code. So I would like to share with you this central question. Why don't we just use types? Why don't we use proper programming languages that are typed in this space? Why are we okay with this fact of life that it's that the helpful hand of compilers and type checkers doesn't extend to the border of our applications and beyond the borders of our applications? At VirtusLab, we wanted to address this specific problem for quite a long time now. We are obviously fans of the Scala programming language. So we started working on it. How long was it ago?
3 years ago.
3?
Or 4?
I think about 4, yeah. So there were a lot of pieces to those puzzles that we had to build, but I think we are getting to a place where we can say that we are onto something that will really help with this kind of problem. We have started with this bit. How many of you have heard about Pulumi? Cool, great, nice. Okay, so Pulumi is an infrastructure as code tool, which is a bit different from other tools in this space because it does allow you to use a true programming language to define your infrastructure. You can use Go, Java, Python, .NET. You can use JavaScript or TypeScript, and also, well, Java is through our efforts because we have contributed that, and then our teams have built Kotlin SDK and Scala SDK. So you can use all those languages to define infrastructure, and Pulumi is very similar to Terraform in what it does and how it works. You just define the infrastructure in the code, actual code, and what it does, it runs this program for you, and it uses this program to manage deployments for you. So it does all the planning, diffs, parallel execution, so you don't have to wait for sequential calls for the cloud APIs. So it behaves like Terraform, but you write actual code to deploy that. So we have built Scala SDK. The code name is Bisum, and that's a synonym of a broom, and it's a play on the fact that Pulumi is also a broom, but in Hawaiian. And this is how the same code looks like in Scala. So we have a task definition for ACS, and we have normal values, like in normal Scala program. We just create actual classes. So everything is type checked, by the way. So it's easier to navigate through this program. It's easier to compose it, and it's just plain Scala that we use to define our resources. So there is already some amount of improvement in comparison to, well, to YAML, obviously, but also to HCL. But, oh, I surprised myself. So let's talk a little bit about what is the structure of this Scala code. So we have resources and we have inputs. Everything that goes into arguments for resources, so the configuration for the actual resource that is going to be created in the cloud, is an input. And then we have outputs. So those are properties that are fulfilled, like promises, so to say, on the resources after the resource has been created. They are asynchronous properties that we get from the cloud once they are populated, once the resource is created. And then we have stacks. Stacks are, well, if we think about a Pulumi program as a blueprint, then stack is an instantiation of this blueprint. It's an actual cloud environment that has been created from this program. Now, Bisum is currently very close to being a fully featured SDK for Pulumi, and it brings this nice feeling that we already know from application development in Scala that, well, if it compiles, it mostly works. Now, if we replace, in this chart, if we replace Terraform with Bisum, does it solve all the problems that we had with InfraLayer being unaware of the application requirements on its own? Well, no, because it is still a tool to manage infrastructure. It allows us to declare it, but it is still oblivious to the fact that there's some stuff in this application. It's just a box for it, black box. It doesn't know what's happening inside. So this talk is actually about addressing this problem. And we would like to introduce this new tool that Michał here has codenamed Yaga. There's a theme, so to say, here. So we have a broom, we have a Yaga, which is basically a witch. And what Yaga is? Well, Yaga is something that is built on top of the puzzles that we have already described. It's sort of a magic glue code that allows your applications to go through the boundaries of the application and infrastructure and exchange information between those surfaces. So if you have applications that are managed by Yaga, those applications will be available to be checked. Information about their types will be available on the infra level. And also the applications, if they talk to each other, they will be type checked against each other. So let's start with an example. We have started our development with AWS Lambda just because the AWS Lambda is a very simplistic API. That's just function calls, but in a distributed setting. And AWS Lambda allowed us to build the mechanics that we needed to make the whole thing work on any kind of a project. Lambdas have very simple request response interface, and they take a simple configuration. This fact is quite important. We'll get to that in a moment. So what Yaga will do for us, well, it's essentially a code generation tool with some introspection capabilities that can take a look into your build published artifacts to extract metadata about the application, about those things that are interesting to us, things that are actually the interfaces of the application, things that are on the boundary. To extract them, to take those shapes, and then use them to glue things together in a way that is seamless and, well, safe. So, first thing that we have to do if we are building those lambdas is that we have to import Yaga SDK into those lambdas. That will do this bit that captures type information about requests, responses, and how those lambdas are configured. I'm gonna go the gentle path. I'm not gonna explain how we do that. Let's just say that we are using some of the Scala metaprogramming facilities to do that. Once the lambdas are built, Yaga extracts those informations that we have provided in the coding model and generates facades for which we can perform communication. So if we have set it up so that the first lambda calls the second one, we'll have a client facade in the first lambda that allows us to safely call the second lambda. Now, we also create resources on the infrastructure level. So the same resources that we have seen before for Pulumi BSOM, Scala SDK, they are generated in the project for infrastructure, and they have the same relationships of dependency as the projects themselves have between them. So you can't configure them in any broken way. If there is a dependency that this project is going to call that project, you have to pass the resource of the deployment of the dependent project to the dependency project. So all the requirements of the applications are reflected in resources, and therefore, if everything compiles together, if the applications compile together with the infrastructure, there is a guarantee that, well, it's not going to fail. So I'm not going to go through this. This is just for any curious mind to take a picture. This is the whole flow as it goes through the integration. And this is not something that you do by hand. There's an SBT plugin. So if you have a SBT project with submodules, you just configure this in SBT. I will show you the configuration. It's not very involved. And then Yaga does this flow for you, and you get a nice workflow in which your IDE shows you, oh, I did change this, and then that broke there. Okay, so demo time. I have no idea if this is going to work, as usual.
If it compiles, it works.
if it compiles. Okay, I have to probably switch this. No. Oh, shit. I broke it. No. Okay. And yeah. Come on. Okay. Can you see that, or is it too small?
It's okay. It's good.
Great. So this is the build SBT file. And how many of you are familiar with SBT? Okay. How many of you think that you are good with SBT? Okay. Considerably less. Okay,
Ask
so
about PTSD, right?
yeah.
The PTSD question is next, yes.
Okay, I'm gonna skip that. So we have 3 modules. So those are projects that are separate compile units. You can see them here. So here's child lambda A, child lambda B, and the parent lambda. And we have this extension that comes from Bison's Yaga SBT plugin. And then we have some additional stuff that is required to actually declare the dependencies. So you can see that we declare that those modules are actually AWS lambdas. And then for parent lambda, which is going to call both child lambdas, one is being called synchronously, one is being called asynchronously. We just declare that there are dependencies. This parent lambda, it has a dependency on child lambda A and child lambda B, and its dependency on of a type of the AWS lambda model. We also have a separate project for infrastructure. So this is the Bison project, also Scala, also managed with SBT, that exists in the directory infra, and it has Yaga dependencies again, but this time they are AWS Lambda infra dependencies, and the package prefix is an implementation detail just for the code generator to know in what package to put the generated code. So we have Scala version 3.3.4, nothing unusual. Everything else is basically covered for you. Yaga SDK that I've mentioned that we have to use in this Lambda brings all the dependencies for the SDK, for AWS SDK on its own, so you don't have to worry about that. You can just program the Lambda. And then we have the code of Lambdas themselves. So where to start? Okay, so we have the parent Lambda declared this way. It's just a class that extends Lambda handler. This is the part of the SDK, and we provide information about the configuration. It's just a case class. It has to derive a JSON format. We have a case class called cooks with just a single argument, str, of type string, and this Lambda returns a string. That's the return type. We have a little bit of a handler code that does things. We create a Lambda client, which is our wrapper for safe interactions between Lambdas, that uses SDK client underneath. And well, what we do, we just call the child Lambda B, child Lambda A, synchronously, asynchronously, and when it's done, we just return a string processing completed. Now, we have a child Lambda A, and we have child Lambda B. Those are very, very simple. The first one just turns the incoming string, which is argument in this event of type B, because this is the input, right? So this Lambda expects this structure to be the request type. So it has to be an object that has a field with name foo of type foo, which then contains, it's an object that contains fields str of type string. And the only thing it does, it just turns this incoming string to uppercase version of itself and prints it to the standard output of the Lambda. Similarly, Lambda B also has a structural input, but this time, as we know, this Lambda B is being called synchronously, so it can return a response synchronously. It returns a response of type buzz, which contains the same string but just reversed. Nothing fancy, just for testing purposes. Now, yeah, it works great. Okay, I'm gonna show you that it actually works, hopefully. So we start the watched infra/compile task, which, as you can see, takes into the account that infrastructure depends on all the Lambda projects, all the Lambda modules. They have to also be built so that infrastructure can compile. Because if we don't do that, we have in the infrastructure layer, we have resources. We have a child Lambda A, child Lambda B, and we have a parent Lambda here. No, not here, here, sorry. And we have to, as you can see, this is the generated resource. We have to pass information about both child lambdas to the parent lambda resource. It won't compile without them. We just can't do this. We can see that if we do something like, let's add something here, baz string. Come on. Okay, so what we get? We get an information that this is a different project, right? This is a different compilation unit and a different resource that is going to be built and deployed. And we can see that we have changed the input of the lambda that is being called by the parent lambda, and now we can see that parent lambda no longer can call the child lambda because it doesn't have the correct arguments here. We could, I think, add this. Was it baz?
It was best.
No, you should.
What? Not the
That should be a field in bar, not
right.
in
outside here. Okay, now it compiles. So we get this, but the more important bit is that infrastructure deployment is also halted. If this doesn't compile, infrastructure won't also compile. Okay, so we go back here, and we can try and see. Well, we can try the black magic, which is actual deployment to cloud on a demo. I know, there's a just recipe, I know. Was it just? Oh, it's not here. It's in SRC? Okay, I'm just gonna use just. Okay, so this is gonna take a little bit of time to actually deploy. But, well, the core point is we have developed a solution that allows us to cross the boundaries between application level and infrastructural level and provide completely new guarantees. That's something that wasn't possible before. You couldn't just describe the interfaces of your application and then have a verification that this application will actually work during this deployment. What's more interesting, the mode that I have shown you with a live deployment with SBT and SBT Yaga plugin, it's nice and useful for daily work. But what is actually important is that it works with any artifacts that have been deployed using Yaga SDKs. So in the cases where you want to do a rollback, but something has already also changed in your infrastructure, you can go to your infrastructure code. There's a field that allows you to provide the version of a Docker image, right? And with all the existing current solutions for infra as code, you just provide this Docker field, Docker image tag or version, and it just deploys that. If something goes wrong, it goes wrong. in runtime when the Docker image is deployed. This is where Yaga really shines, because it will actively prohibit you from deploying something that doesn't work with the current version of the infrastructure. Okay, and now we hope that AWS doesn't fail. Oh, come on. Cool. It seems that we have managed to get to the other side. So I have prepared a small AWS Lambda invoke command just to see that it is in fact working. It's JVM, because building native images, something that we're working on currently, because Lambda should be small and fast. It works, but deployment time is much longer, so it's not really talk friendly. 200. So it didn't crash, and that's a relief. I don't think I have to do this way. No. No idea. Where is it? Oh, no. No. Where's the browser? I have no idea where it is. I've lost the browser.
Do you have free virtual desktops?
Yes.
Oh,
Okay. Yeah. I wanted to go here, actually. So this seems to be now. And yes, well, our request is here. So it does work. Okay. We can also see that in the Pulumi cloud, we should have a project with the deployment in a stack dev. We have deployments? No deployments. Oh, wow, cool. But there's an update. Okay. And we have our deployment in cloud. So anyone else can now do an nasty trick and just click destroy somewhere here. Okay. So back to the talk. So are you going to show? No. How do we live with those tools like that? Okay, so the whole approach that I have just shown to you, it's probably not limited to Scala only. We didn't test that yet, but there doesn't seem to be any hard limitation to supporting other languages. It is completely possible to build the integration layer, the glue code that is used by Yaga to extract information. If we can capture information about the interfaces that other languages, other applications written in other languages have, it should be possible to generalize this approach to other languages, to have interop between different languages. In Scala, it's actually much easier because the language is very static. It's there's a lot of information available statically, and therefore it's easy for us to capture that with tooling that is provided by a Scala compiler team. So if we have this way to capture this information, we can integrate this for other languages. It can be integrated into other build tools. Any build tool that has a proper graph of modules that can be extended with some additional information would suffice. And I also wanted to say that we aren't the only people in the world that are insane enough to build something like that. there's a project called SST. They support TypeScript only, and they seem to be focused on applications that use Node.js frameworks, mostly Next.js and things like that. But they do have some similar concepts. I dare say that our is more future-proof because they only work in this live mode, and we provide the way to work with versioned resources, versioned artifacts. So you can use something that was built a month ago, and I don't think that's possible with their approach. And I think that's it. Thank you.
Do we have any questions? Yes.
Yeah. So great presentation. It looks amazing. I noticed that the lambdas are all in single project.
Mhm.
Do you have anything like if I have a bunch of lambdas in my team and someone else has their own lambdas in their own repository?
Mhm.
How does that work cross repository? Is there anything is
Okay,
there a solution or something that you plan?
Yeah, it is possible because you can reference an external artifact. It just has to use the SDK, right? Because the information is captured and then stored in the artifact in a way that our integration can then extract that information. You can inspect into, let's say, Docker image or a jar. If you have something like that, we can extract the information. We are working currently on integrations to different distribution systems and different interfaces. So next on the playlist is obviously HTTP APIs. So we're currently looking into how we can integrate with Zapier because this is the most common choice currently in Scala. But other platforms, other interfaces are coming. And if somebody builds something like that with an SDK that is compatible with Jagan, you can reference that artifact in your build. And if your deployment, somehow the integration between your applications is broken on your side, you will see that in your deployment. It will stop compiling because, oh, the new version that they have published, you replace that in your deployment, and then it no longer compiles.
I see. Thanks.
Any other questions? Yeah.
Are you able to also, at the moment, check if all the infrastructure for your application is, complete? So you have all the databases and such.
That's part of the interfaces. So we are going to provide some kind of wrapper SDKs, additional SDKs for resources that you want to use. For instance, Kafka, for instance, Postgres. So it's still something that has to happen because there's just a lot of that. At the point where we are, we have tried out the mechanics that allow us to glue everything together and make it work in a nice way. But now there's the time to build all the integrations. So it's the current phase now.
Maybe one question from me. What was in the just file?
Oh.
Maybe you could explain that.
Just file is just a make file for hipsters. So it's just a make file.
Okay, so maybe let me step in a bit. So basically, if you want to set your infrastructure up, you just need to call Pulumi up command, which then does all the magic that Pulumi offers to you. But basically, what it does is first it tries to inspect your project to find the right build tool to build everything, and then it runs your infrastructure. If you have a SBT project, it's kind of tricky because in SBT you can have multiple modules, so you need to somehow tell Pulumi which module is your infrastructure. So for this you just need to specify this environment variable.
Yeah.
So this was a simple helper like that.
Yeah. We could basically just copy paste this, run this in the terminal, and it would be exactly the same thing. Okay, thank you again.